So once again, let me give a brief back at the functions that we've been through, and then those that we have found the derivative of the formula. So we look at the polynomials, right? And these got the power forms, right? Like, so that's why we have the power rule came in for handling these polynomials, right? Because we got the x to the n power involves in your polynomial, right? And then the power rule can also be used for your rational function. Right? And then in the rational function, you know, sort of like additionally, we have the quotient rule that's used for this, right? A lot of times we use the quotient rule for that. And then we advance to the trig function. Right? And we learn specifically rules for sine of x, right? Derivative of sine of x, cosine of x, right? We got tangent of x, cotangent of x. We learn about secant of x and cosecant of x. Right? That's the trig function. And then we moved over to the logarithm and the exponentials, right? The logarithms. Okay. We learn all of these specific rules for all of those. See what I'm saying now? Okay. Quotient rule, all of these. Got it. Okay. And then product rule also apply for the power rules going together with the product rule over here, right? Here is sort of like the power rule. Using that together with the quotient rule when we handle the rationals. So now the next family of functions that we haven't had our chance to get into, now we're starting into it today. We're looking at the inverse trig function. Okay, the inverse trigs. Like those sine inverse, you guys learned about that back in pre-calculus 2, right? The sine inverse of x and the cosine inverse of x, right? And we will get to the tangent inverse. There's a cotangent inverse as well. There will also be the secant inverse, okay, and then the cosecant inverse. Okay. The 6 fundamental trig functions, they all have their inverse functions. See what I'm saying now? And that's what this is what we are heading into now for the big star. That's our goal for that family, right? And then as we finish moving through these guys here, then we have covered the derivative rules for all families of functions, and then we're ready for heading into the application of that. We're looking at learning how to find the derivative, right? Derivative of inverse. We will study how we can find their derivatives one by one. So let's start out with, we're going to have y equals sine inverse of x. Right? Let's find its derivative. Our goal is to find y dx, the derivative of our sine inverse function. It's not even an example, it's just one famous problem, and once we finish with the final outcome again, right? Once we come to the final outcome, that will become our rule for finding the inverse function. So now think about it, finding the y dx, right? Y equals sine inverse of x. So that means from your pre-calculus 2 days, the days that you guys were learning about trigonometry, when you say a variable y equals sine inverse of x, that means the same as sine of y, right, equals x. You guys agree? Right. So that relationship, that backward relationship, is not a surprise for any one of us. So we got to take pre-calculus 2 before we got into here, right? So now sine of y equals x. Sine of y equals x. And I'm seeing this y now as some implicit function of x. We already knew that sine is the inverse function of x, but I have purposely rewritten that into this form so that I'm seeing x and y are some two variables, and then y is an implicit function of x. So from that way, I'm going to use the implicit differentiation idea again, right? I'm going to differentiate both sides in respect to x. Differentiating both sides, the left-hand side and the right-hand side in respect to x. I'm treating y, right? So the plan here is y as an implicit implicit function, right, of x. That's the idea of it. So now in that way, so hopefully you guys have gotten a decent level of fluency in terms of implicit differentiation. The right-hand side is the easier side, right? It's already explicitly written as in terms of x, and we want to differentiate, take the derivative in respect to x. So that term right there gives me the derivative being 1. This function here, y, is some function of x. We just don't have to know what it is, right? Some function of x. But the sign of y means it's sine of some function f of x. Go with that there. Okay. So that's why, once again, there's outer function and there's inner. So there's the inner function and there's the outside function. Right? Chain rule is going to come in. So now I'm seeing that the derivative for the outside function gives you what? Cosine of y. Right? But then we need to multiply with the derivative from the inside function. And again, even though we already had our beginning the understanding of what y is, but we still purposely seeing y as an implicit function, as some unknown function. So the only choice we have, if we don't know function y, its derivative is just some implicit dy dx. So chain rule says the derivative of the outside multiplied with the dy dx from the inside. Okay. And so now here's how I'm seeing it in the next step here. Yes, so now I'm going to solve for dy dx, because our ultimate goal is to find dy dx, right? So finding dy dx, I'm dividing both sides by 1 over cosine y. Right? And so now, there are many ways to argue this. On one way, you can see this. Now, I got to remind you one thing. Now, if y initially defined as an inverse function, right, and that means the input actually here can only be anywhere from -1 to 1. Remember that the input domain for your inverse function right there. And so, and the y value, the output range for your inverse function only comes out anywhere from -π/2 to π/2. That's something to know about your inverse trig function. Yeah. You guys follow me on that? Okay. The y value for an inverse trig function is anywhere negative and goes to positive and negative π/2 to π/2 only. Right. So now, from that way right here, here's how I'm seeing it. One way to argue it, because our derivative at this point right here is in terms of y only. Right. And that's ugly. That's not the usual formula we want to see. You guys can put me on that. Yeah? So here's how I'm seeing it. Now, don't we famously know that sine square of whatever angle, so let's call it sine squared of y, okay, plus cosine squared of y, right, equals 1, and we always know that famously from trigonometry. And we have been using that understanding, right, throughout our classes, scattering. So sine square of y, isn't that x squared? Because sine of y equals x, right? So sine squared of y, I have an x squared here. You guys repeat that? Right? And that's plus cosine squared of y equals 1. And so I'm going to subtract the x squared from both sides, right? Subtracting x squared from both sides, it leads down to, so we're currently at this equation right here. I was bringing up y squared, sine squared of y plus cosine squared of y, right, equals 1. So here, yes, sine squared of y equals x squared, okay? And then that's plus cosine squared of y equals 1. And so now I subtracted both sides of the equation by x squared. That leaves me behind cosine squared of y equals 1 minus x squared. And so now cosine squared equals, cosine squared of y equals 1 minus x squared, meaning cosine of y by itself, right, can be solved for by taking the square root, right? And in algebra, we famously take the 2 square root plus and minus square root, right, of 1 minus x squared. You guys following? But then, because remember, I put that on that other board earlier. The reminder was saying here is that the y value, now y initially was defined as a sine inverse, so y has to come out with value anywhere from -π/2 to π/2. Y is an angle that comes out anywhere from -π/2 to π/2. That means that means your cosine of y over here. See, if y is a value anywhere from minus pi over 2 to pi over 2, think about, see, at least when I was teaching my own the trigonometry class, and I always keep having my students focus on the unit circle right there. So from minus pi over 2 is down here, and then pi over 2 is up here. See what I'm saying now? And that's the half right-hand side on the unit circle. So if we are anywhere in that, then the cosine value is positive. You guys follow what I'm saying now? So because the angle is anywhere from minus pi over 2 to pi over 2, right? The cosine value has to be on this right-hand side, right? It's positive. So that means here that led us to that decision. We got to take the positive. So cosine of y equals a positive square root instead of the negative 1. Right, you guys with me on that? Right, so that leads down to, yes, now cosine of y equals the positive square root of 1 minus x squared. Okay? So that's one way of arguing it. So now that means what? Back to our derivative step that I was finding. So I was up to this point right there. Right? And I kind of split out using some scratch word for this. But cosine of y is now square root, the positive square root of 1 minus x squared. So the final derivative. dy equals 1 over square root of 1 minus x squared. So now we have found the derivative for the sine inverse of x. Okay. And then arguing it using the trigonometry identity right here is just one way of seeing that. Just one way of seeing that. Okay. Now once again, if you can also argue in a different way. That's another way of arguing it. Just think about your angle over here. Yes, the angle y that came out from sine inverse, right? Is some angle from minus pi over 2 to pi over 2. Let's purposely pick an angle, because pi over 2 means a 90 degrees angle, right? You guys agree? Right. So let's draw that in a triangle, and then that triangle can generalize the idea again. Y is some angle here, right? And then so y being some angle, then sine of y equals x, right? Think of that as x over 1 again. You guys would be on that again. And so that's why the sine in a right triangle is famously known as opposite over hypotenuse. Opposite over hypotenuse. Sounds good? That means I can put, so with sine, I mean with y being, you can just draw that there, put that there, you know, arbitrarily. And x has to be the opposite. And 1 is the hypotenuse. So now, if on this triangle, if your hypotenuse is 1, it's a right triangle, and one side being x, how do we find the other side over here? Being a triangle, what do we have? On this side over here, according to the Pythagorean theorem, you can call that some side z again, right? X squared plus z squared equals 1, right? 1 squared. That's why the unknown length z right here, again, z equals the square root of 1 minus x squared again. It was technically plus and minus square root, but then it's a triangle, and we purposely put that in a triangle, so I was using the positive length, yeah, so it's a positive square root. So that's another way of arguing it. Yeah. So this is now cosine, because the adjacent right here is what cosine of y is adjacent over hypotenuse. That's why in this triangle right here, the z right here is the cosine of y. That's another way of arguing it. This information indeed, back in the days of your pre-calculus 2, it should have been taught as a chosen one. The actual sine function goes like this, right? And so pi over 2 is here, minus pi over 2 is here. So now when we take the inverse, we have to only pick this portion right here so that we can take the mirror image of that. And so let's make your sine inverse graph going. I mean, it takes some long story to go back to that. But so your sine inverse, right, goes like this. Think about you draw the sine wave along the y-axis, but if you're drawing it like that, right, take the whole sine wave and draw on the y-axis, then it's impossible because it's not even a function. So we only take that in between that. Right? So -1 is here, 1 is here for the inputs, but then the output only comes out as low as the negative pi over 2, and as highest is pi over 2. And that's the idea. Yeah. So as far as a derivative rule right here, then I have found the sine inverse of x, right? Taking the derivative will give me just simply a 1 over the square root of 1 minus x squared. That's the derivative for sine inverse. Or the short form of that, the short form, like many cheat sheets been writing, right? Like the cheat sheets have been selling at bookstores and things like that. The sine inverse of x. So I take the prime, it gives you a 1 over the square root of 1 minus x squared. See what I'm saying? Now, those are the short form of that. Okay. So now our next direction. What about the cosine inverse of x? That's another well-known inverse trig function, right? Let's learn how we can find the derivative dy dx. So, learning from the earlier experience, let me introduce some information, some preliminary information regarding the cosine inverse before we get it. See, when you define a function y equals cosine inverse of x, right? Then the input x here got to be anywhere once again from -1 to 1. But then the output for y here as an angle comes out. It's not from -pi/2 to pi/2, but it's 0 to pi. Okay. So think about there's your x-axis, y-axis. You see cosine inverse of x equals y means the same as x equals cosine of y, right? So think about, you can draw the cosine graph on the y-axis here. Treating x as a function, draw the cosine graph on the y-axis. It's kind of look like that. See what I mean? Right. But that's failing a function, right? That's failing being a function. That's why the cosine graph right here, we only take the portion that, see, I was a little bit off scale right here, but we only take that portion. See? One is here, so the input, the actual cosine inverse is this piece right here. Right? You guys agree on that? And then the highest it reached, vertically, it's a pi, and the lowest on the y value right there is a 0. See what I mean? That's the whole reason why. But once again, as far as the more detailed explanation, you got to review the pre-calculus too, the trigonometry stuff. Right? And that preliminary information is useful for this right here, because y now our m is y as a function cosine inverse of x. So we're gonna purposely rewrite it as cosine of y, right? Equals x. That's my starting point again. Okay? And so now I'm gonna see y as some implicit, right? Y as an implicit function of x again. Right? Y is just some function, right, of x, implicit. We purposely turn our focus in that direction right there, right? We purposely tweak our attention a little bit. So now I'm going to differentiate both sides. So from where the cosine of y is, right, I'm going to differentiate it with respect to x, right? And the right-hand side equals x. I'm going to also differentiate that with respect to x. You guys agree there? So in my next step, these are just extra notes to remind you guys when you write in your written step, you don't need to always include that. So the right-hand side give me what derivative is that? It's just 1, right? The left-hand side here, we got outside function. See, because y equals some implicit function of x, meaning cosine of y means we apply the cosine operation, right, on top of our implicit function f of x. Are we good with that then? So that's why now there's inside being the implicit function and outside being the cosine. So taking the derivative of cosine, negative sine, right? Okay. Negative sine of the whole y function implicitly. And we multiply with the derivative of the inside again, giving me just the unknown y dx. So that product there, according to the chain rule, now equals, and then equals 1. Okay. So we found we have successfully differentiated both sides in respect to x at this point here. And so now I'm going to solve for dy dx, right? Just like usual, I'm going to go dy dx equals 1 over, right, the negative sine of y, because I was dividing both sides by minus sine of y. See what I mean? Okay. To arrive here. So one more time I'm going to show, but see, we don't like this answer because we finished our work in terms of y, right? Our function from the beginning was in terms of x. So we purposely treat our function implicitly, but it did have a definition, right? An explicit definition. So we need to go back to that beginning one. But now we're ending up with sine of y. So how do we find that other one? Okay. So you can go with two different routes with that, right? One way, see, keep in mind with that information right there. Sine squared of y, okay, plus cosine squared of y will famously equal 1. Like, no one can argue about that. And so in that way, cosine squared of y equals, because cosine of y itself equals x, right? And so cosine squared of y means we've got x squared here. So x squared plus sine squared of y equals 1, right? And then we can do the usual solving work here. That means sine squared y can be found by subtracting x squared from both sides, right? That will be making it equal 1 minus x squared. We good with that still? So now I'm going to take the square root of both sides. Sine of y comes out getting plus and minus square root of 1 minus x squared, right? But so once again, between the two square root answers here, sine of y can equal to positive or negative square root of 1 minus x squared, right? Which one is the right one? Which one is the appropriate one for our case right here? We need to rely back on this, right? Now y itself, right, is known to be an angle. Now through the cosine inverse, y comes out being an angle anywhere from 0 to pi. The angle from 0 to pi means on the unit circle or on the end circle, right? It's the upper half angle right here. You guys follow me on that? Zero angle is here, pi is right here. That's the upper half angle. So anywhere you're in the upper half angle, quadrant 1 and quadrant 2, then the sine value is the vertical, sine value is the vertical, right? Is it positive or negative? It's positive, right? So sine value, sine of y has to be positive. So that's why it leads us down to choosing a positive square root choice again. Right? So that means sine of y is chosen to be the positive square root of 1 minus x squared due to the angle description again, the quadrant description. You good with that? So that means back to the work right here, I'm advancing to the next step, the dy dx can now be a d. See, I'm going to put that, because I've been focusing only on the sine of y, right? I kind of ignore the negative, so the negative can be purposely put in front, okay? It's a minus 1 over square root of 1 minus x squared. You guys see that there? Okay, so now we have derived another formula for the derivative of this inverse trig function, inverse cosine function. So in that way, we can put that here as another formula for us. Okay, so when our function is a cosine inverse of x, right? Differentiating it or taking the derivative of that, it gives me negative 1 over square root of 1 minus x squared again. Right? Or so that's one formula, right? Or we can just use the short formula, cosine inverse of x. The prime gives me negative 1 over square root of 1 minus x squared. Right? But two separate formulas, you know. And then this is just for your comfortability right here, but the way how I derived from sine of y into the square root of 1 minus x squared, right? That way was just basically using the trig identity. If you're not comfortable with that, you can use a triangle similar to what I was pointing out earlier. So think about a triangle just like that, right? The angle is anywhere from 0 to pi over 2. That's your angle right there. Y. So cosine of y equals x, right? Cosine of y equals x. So that means you can always put cosine of y equals x. Y is the angle. So cosine of y equals x means it's adjacent over 1, right? I mean, it's always 2 over 1. So adjacent over hypotenuse. That's what we famously know about cosine in a triangle. So we put 1 here on the hypotenuse, right? And we put x here. Right? So that means what? According to the Pythagorean theorem, the unknown length z right here, we got to go x squared plus z squared plus equals hypotenuse squared, right? Which is 1. And so z itself right here, okay, z squared is 1 minus x squared, right? And then that leads down to finding z value. Technically, it was a positive or negative square root, but then it's length here, so we only take the positive root. Okay? making it 1 minus x squared. And so the cosine of y, so sine of y right here that we're looking for, this quantity right here is 1 minus x squared in the square root. And sine of y has to equal what? Opposites over hypotenuse, right? That's why it's 1 minus x squared. Right there. That's another way of arguing it. So you got your different routes of understanding it. All right. And then let me bring that into another one here. You guys ready for it? Because we found the two formulas. So what we have here is how about y equals the tangent inverse of x. And so again, a couple of preliminary information. When you have y equals tangent inverse of x, that means the same as tangent of y equals x. So y is coming out from an inverse function. That dependent variable right there must be an angle. Right? And so tangent inverse of x coming out equals y, that means y is the angle. So now on the other way around, tangent of y, tangent of the angle y, right, must equals x. So that's some understanding from that trigonometry. And then the input x here is anywhere in the domain from minus infinity to infinity. Okay. But the y value is only anywhere strictly between negative pi over 2, the angle that comes out from the tangent inverse, strictly minus pi over 2, pi over 2. Okay. So that was information that we've learned from pre-calculus 2 right there. And then we can derive it right here. So, once again, to find that derivative, y equals tangent inverse of x means tangent of y equals x. Right? And then so now I'm seeing y as an implicit function of x, all of that same exact idea that we're going with implicit differentiation. And so I'm going to take the derivative, both sides in respect to x. So on the left-hand side is the derivative of tangent. On the right-hand side is the derivative in respect to x of the x term again. I think you guys will remind you. What's the derivative of tangent? Was it too long ago? Yes?
Secant squared.
Secant squared, right? All agree? Secant squared? All right. So that means taking this. And by the way, the easier side is on this side right here, differentiating in respect to x, right? So that gives me a 1 right here. But that one right here, tangent is only the outside function, right? And then in the inside we got an implicit function. So I've been repeating that idea so often, so allow me not to keep mentioning it, right? So secant squared is the derivative of the outside function. This outside function we got a tangent, secant squared of y. You guys with me there? But then multiply with the derivative of the inside implicit function right there. It's going to be some dy dx. So it's secant squared of y, right, times the dy dx. So that means now in the next step I can just divide both sides by the secant squared of y, right, to solve for the dy dx. So dy dx will come out getting positive 1 over the secant squared of y. And then let me remind you guys another important trig identity right here. Back in the days that you were learning trigonometry, that you see secant squared, right, of any angle will always equals 1 plus tangent squared of the same angle. You guys got that reminded? Or remember that still? Or right now it's just a reminder, right? So it's an identity, meaning it will always be true for regardless of whatever value for y is. So secant squared of y equals 1 plus tangent squared of y. But tangent squared of y means what? It's 1 plus. I mean the tangent squared of y is the x squared, right? Because tangent of y equals x. So tangent squared of y equals x squared, right? So that means in the end, secant squared of y that we have come down to in our final derivative here, secant squared of y equals 1 plus x squared. And so now we have found it. It's just all in that purpose that, hey, we don't like writing our final derivative in terms of y because our starting function was in terms of x, right? So the final function here is 1 over 1 plus x squared. You know that, okay? This is the derivative for tangent inverse. So in that case, we have a third formula. when our function is a tangent inverse of x, right, differentiating it is going to give me simply 1 over 1 plus x squared. So this is another highlighted formula right there. And then as a shorter version of that tangent inverse function from where that is, take the prime, right, that gives me 1 over 1 plus x squared. And then again, I've been giving two different interpretations of that, but so using identity is one way. You can once again remember y is an angle, right? You can use a right triangle. Put the angle y somewhere, right? So with this triangle over here, think about it. You got tangent of y is opposite over adjacent, right? So opposite adjacent, tangent of y equals x means tangent of y equals x means you can purposely put that over 1. That's why I'm seeing that ratio over here as opposites over hypotenuse. And so on my triangle, my right triangle, after making an angle y again, adjacent is 1, opposite is x. So Pythagorean theorem says what? That hypotenuse, which is unknown this time, right? That one has to be what? 1 squared plus x squared, which is 1 plus x squared. It's right there. See what I'm saying there? So that's another way of arguing it. If you don't remember all of the identities. Sound good then? But you must remember the Pythagorean theorem. Right. So now the last one for this list of inverse functions. Now, cosecant and secant inverse. Usually the students, and those are still some challenge on their own at some point. So usually we only stop at cotangent inverse, and that's good enough for that. Okay. But we don't have to go all the way to secant inverse and cosecant inverse. Right. So once again, our understanding here, we have the function defined as cotangent inverse of x. Right? That's fine with the derivative. So see, if y equals cotangent inverse, okay, trivial information here says it means the same as cotangent of y equals x. Okay. And then the input for cotangent inverse, the input x for cotangent inverse goes anywhere from minus infinity to infinity. It's a large interval, yeah, right? That's the entire real value interval. The output, right, goes strictly between 0 and pi. Okay? 0 and pi. So now we're going to get into finding the derivative here. So starting out again, the cotangent of y will equals x, right, from that relationship. So I'm treating y here as an implicit function. So now I'm going to differentiate both sides. Left-hand side here, I'm going to differentiate in respect to x. The right-hand side is the x. I'm going to differentiate in respect to x as well. Okay. So the right-hand side, the easier side, gives me 1. Right? That's the term was already in terms of x. Taking the derivative, that's 1. On the left-hand side of here is cotangent. What's the derivative of cotangent? Yes?
It's negative cosecant squared x.
Negative cosecant. But here's y, right? So it's negative cosecant squared of y, the inside function, right? Because we're taking cotangent on top of some implicit function. But that means what Chamberlain says we have to multiply with the derivative dy dx. See that now? And yes, I'm going to divide both sides by the minus cosecant squared, so leaving it minus. I mean, dy dx here is negative, right? 1 over cosecant squared of y. And then once again, you got a couple alternatives for you to, because we don't like having final answers in terms of y. So again, cosecant squared of any angle, right, equals 1 plus cotangent squared of the same angle. That's a reminder from trigonometry. So that comes out quite easily. Cosine squared of y will equals 1 plus x squared. Because in our case right here, cotangent of y equals x, right? So cotangent squared in the additive will become x squared. And that's how, now I've found it. dy dx equals negative 1 over, now instead of cosecant squared of y, I'm writing that as 1 plus x squared. Okay, and we found another derivative. So the tangent inverse, when you take the derivative, it's just the positive 1 over 1 plus x squared. And then the cotangent inverse, taking the derivative, it gives us that thing that you're seeing on the board. Now, there's another final formula here, cotangent inverse of x, right? When we differentiate that in respect to x, we come out with negative 1 over 1 plus x squared. That's another formula that deserves our attention. And then here I'm looking at the short form of that, cotangent inverse of x, right? Take the prime, gives me negative 1 over 1 plus x squared. Okay? Let's look at one example, a couple of problems. Example 1 here. Let's find the derivative from x or y dx. Right? Part A, our function here, y equals this is sine inverse of 3x to the fourth. So we have the derivative for sine inverse of x, which is quite simple, right? We will never have to deal with hey, just the straightforward. What's the derivative of sine inverse? Because you can just repeat whatever we have written down here as a formula. The real challenge here is that our sine inverse now take some 3x to the fourth inside of that. See what I'm saying now? Right? So we recognize that nature, and this is sort of like the thought process here. Inside, I recognize some g of x, right? Being 3x to the fourth. You guys follow it? So there's your inside, right? And then we're taking the outside function on top of that. See what I'm saying now? So from the outside function that I recognize here is simply whatever some capital F, I mean some f of capital X, right? Being the sine inverse of the whole argument x. Okay? So now realizing that nature, having the inside and outside, now we can use the chain rule. And the chain rule up to this point hopefully is something that's reasonably fluent for you guys, right? So taking the derivative. So the y dx here, right? Chain rule says we take the derivative of the outside function first, right? So the outside function is a sine inverse. So the formula was just written down on the board. That 1 over square root of 1 minus the whole thing inside of that. But our inside this time is a 3x to the fourth. Now I'm looking at subtracting the 3x to the fourth quantity squared. Okay? That's the inverse trig function's derivative as the outside function. And now we multiply that, right? According to the chain rule, we multiply with the derivative of the inside. Our inside is right here. Right? Our inside is right there. So 3x to the fourth, taking the derivative. 3x to the fourth, we're taking the derivative. So in the next step, it comes out 1 over the square root of 1 minus 3x to the fourth, all squared in the denominator. And we multiply that with so this derivative now gives me a 12x cubed, right? So all together it comes down to, see, we're putting that all in one fraction. It's 12x cubed, and dividing that by the square root, 1 minus, right? And then here it's going to be 9x to the 8. That's our final answer. The squaring that 3x to the fourth, right? It's going to give me 9x to the 8. Okay, so let's continue with that example 1 that we were having. So let's look at part B. So go ahead and spend some time writing it down. Okay, so we've learned about the rule for taking the derivatives of inverse straight functions. Right? So what I'm seeing here in this problem, we have a product, right, between some function with two trig terms together, and then in product with a inverse straight function. So taking the derivative, it can be quite straightforward here. Recognizing the product here, I'm going to apply the product rule. Right? So we first need to take the derivative of this. So 2 sine of x plus 7 cosine of x. Here we take the prime of that. We'll multiply with the other function without prime, right? And the product rule says we further must add, and now I'm going to take the derivative. I'm going to leave the 2 sine of x plus 7 cosine of x by itself right here, no prime, and I'm going to take the derivative and multiply that with the derivative on the tangent inverse. Right? So that's the setup for the product rule. And so now we're going to go ahead and, according to this instruction, right, to this indication, we're going to go ahead and take the derivative one by one. So that prime here on the first function with two terms. So we're going, okay? That first term becomes, anyone? 2 cosine of x, right? So 2 cosine of x. That's the first term, right? The next term, it's adding 7 cosine of x. Now taking the derivative of that. Anyone else? Yes?
Minus 7 sine of x.
All right. And we multiply that derivative. So this is the derivative from that earlier step, and then we multiply that with the tangent inverse of x, right? Right. And then we add it. And now the next part here in the product, I'm going to keep that the same, 2 sine of x, right? Plus 7 cosine of x. And so we freshly learned, we just recently learned about this. So anyone remember from the notes, derivative of tangent inverse? So that becomes 1 over, right? 1 plus x squared. We wrote down those rules together. Okay. And for this problem right here, I mean, I just want to focus on the particular skills of being able to get the derivative on each of those little components. So how about I'm going to go back and put in this additional instruction right here that do not simplify it. Okay? So I need you to simplify it. So for this problem, so if that was the additional instruction that I now put in, then we are good here, right? Without the need to simplify the expression. Okay? It's not really that easy to simplify this thing anyway. Tangent inverse of 5 sine of 3x. So 8 times that. All right, so go ahead and spend some time writing it down. So this one here before we start, so I just want to point out, so this is something to explain for you in your thought process that you can explain to yourself, okay, right? We got, see, there's a 3x, right, being inside of some sine of x, okay? So we got outside here, we got the inside of that, right? But then we got even further outside of here. See what I mean? Okay. So now, outer, right? So there are some levels of inside and outside of that. That's something to point out. So now, let's handle that one by one. So from the inside out, so where I pointed out that we got the 3x being inside of a sine, right? And then it's 5 times the sine again being inside of a tangent inverse, right? And so now in that way, now let me roll back to that beginning point right here. Okay, so that function now, when we take the derivative, so the first thing to isolate your attention right here, I'm seeing the entire 5 sine of 3x and here being the inside, some big inside of the tangent inverse, right? So I wrote this here earlier and I had to erase it, kind of revise my the planning right there. So the outside function is a tangent inverse, so we learned from yesterday. 8 times, right? What's the derivative of tangent inverse? Okay. Now, 1 over 1 plus x squared, right? But now we no longer have x squared, we replace the x with all the whole ugly thing right here. So it's, I agree with you, 1 over 1 plus, right? But instead of the usual x squared, see we got the whole 5 sine of 3x all squared. So that's the tangent inverse, keeping the entire inside part the same again. But that's only half of the story, right? So now the chain rule says with that inner part right there that I'm pointing out, we've got to take that derivative. So now how about as a plan over here? I'm just going to say that the next step is to find the derivative on the 5 sine of 3x. That's what we need for that. Okay? But then now further on this function, see I showed that earlier, but now breaking it down into little steps here sequentially. See, we took the derivative on the most outer step, on the most outer function, and now we are about to take the derivative of that inside function. Right? But then that whole function here, now I'm seeing the 3x here as the inside, and then there's the sine of x, right? Being the outside of your function again, right? So now in that case, now I'm ready to complete. So, well, the whole thing here is just h, right, times the big fraction, 1 over 1 plus, right, the 5 Cosine of 3x, should have used brackets here. Square, right? Now multiply. So now this derivative of sine of x, anyone? Cosine of x, right? Cosine of x, but is this really cosine of x in here? It's cosine of what? 3x. So it's 5 times the cosine of the 3x. That's the derivative of the outside, right? And then we multiply that now with the derivative of the inside, which is now quite easy, right? That derivative now gives me just simply 3 with that 3x, taking the derivative, gives me 3. So now we are ready to, and at this point we have officially, we are officially done with taking the derivative. Okay? Ready for just putting it in a more simplified way right here. And there's not really much, anything to simplify, but we can combine the coefficients, we can multiply all the coefficients together here, right? Making it a big coefficient right here. So for the 8 times 5 is 40, multiplied with 3 together, right? Making it 180, right? I mean 120. So I got 120 cosine of 3x to be put in the numerator, and then in my denominator. And this overall, this square on the whole 5 sine of 3x, so here I can put that as, so 1 plus 5, okay, actually it's not 5, 25 sine squared, right, of 3x. See what I'm saying there? Right? That's making it to look much better. So now we have found that derivative. For example 1, I think we have seen enough problems with that, right? It's focused on just how you apply it, bring in your skills with the various different inverse trig functions, and then combine that together with those other functions you guys have learned. Right? And actually, at this point, you guys have learned all of those different skills, how to find the derivative on different kind of function already. We've learned all the way from the power rules, right? And then there's what the trig and the trig functions, right? Quotient and product rules, right? And the chain rule, and then the logarithm and exponential. And now we're looking at the inverse trig. Right? So you really have found the way to calculate the derivative for all of those. But so before we be done with this, how about let's look at example 2 here. Right? So let's find the equation of the tangent line. All right. Okay, had a problem written down so far. So it's another tangent line problem, and like I said earlier in the quarter, I will keep getting back to a tangent line problem, because the whole purpose, everything we've learned so far, we're going through so many derivative rules, they're all serving that one purpose. We find the equation of a tangent line, and you guys are getting close to that day where we start learning why tangent line is so important, why tangent line problems so matter to us right here. But right now, let's just keep building out the essential skill again. Okay. So remember, we always got 3 major steps for that, right? And the tangent line we're about to get will always have that line of famously equation. I mean that equation famously to be y equals what? mtx, right? Plus c. You good with that then? Right. And so in that way, let's first find the slope right here. And we're on our way to find an mt. Right. And so, but to find the derivative, to find the slope of the tangent line, right? The first thing, yes, we need to obtain the derivative for our function. And now our function, see, different tangent line problem apply to different kinds of functions. Like we come up with different derivative rules. So our function here is a tangent inverse, right? Right? Remind me again. It's just that one very basic rule again. So anyone else? Yes?
1 over 1 plus x squared.
1 over 1 plus x squared. I heard you. Right? Look good? So you got the derivative. So that means what? The slope of the tangent line can be calculated as easy as just substituting that given value, right, into your derivative. So that you got f prime of 1. And that's making it what? 1 over 1 plus, right? 1 substituted in for the x, so making it 1 over 1 plus 1 squared, right? Which is making it simply 1/2. You guys can go ahead and check my calculation and all that, right? So now we got a slope. So that means at this point right here, our equation is sort of like, this is just optional stuff, okay? It's just my explanation. So the equation is halfway completed, being a 1/2 x, right? Plus some unknown y-intercept. Okay? And so the next big step right here is to get the tangent point. Right? So the tangent point. Okay, so when x equals 1, how do we calculate the y value for the tangent point? What do we do again? Yes?
Plug in the x value into the f of x function.
That's right. You substitute. So to get the y value, you're substituting the given value, right, into your original function, right? And so that way we're looking at tangent inverse of 1. Okay? Let me branch out on scratch work right here and ask you guys one quick question. Okay, try to do this without your calculator. I mean, this should have been stuff from pre-calc 2, but I want to get you guys a little bit of a review again. How do you calculate tangent inverse of 1 without a calculator? Well, whatever that answer is, we call that some angle x or some angle theta, whatever you want to name it, right? But how did you get that x? Yes?
We turn it into a regular tangent by saying tan of x equals 1.
Right, okay. So you turn that into tan of x, right? Equals 1, and the point is at which x angle, right? Making tangent of x equals 1 right there. Yeah, so we're looking for that, what angle that angle x again, right? Making tangent of x equals 1 again. So what angle is that? Okay, think of the unit circle, yeah?
45 degrees.
Yes, the 45 degrees, yes. Okay, I agree. Now, in radians, what's the 45 degrees? 5 over 4? Yeah, so that equation, right? Ultimately, we're looking for which angle x equals 1. So the angle came out 5 over 4. Try to go as much as possible without as far as possible without a calculator. That gets your skills sharp enough for that. See what I mean? Okay. You may think, it's too crazy to make you guys do that without a calculator, but there's always a good reason behind the scenes. Okay. All right, so we found that means what? Substituting x equals 1 into the tangent inverse. Here, our y value for that state, right, is 5 over 4. So now we have completed our tangent point. It's at 1 comma a pi over 4. Good. So now we got the tangent point. Okay, so in that way, what's the next step here? Now we've got the tangent point, so the last step here is just finally complete the equation, right? Our equation now really, as a big reminder, is a 1/2 x plus with some unknown y-intercept, right? That's halfway completed, so now we're substituting in the tangent point. X for x, y for y, and that was 1 for x and pi over 4 for y. So I'm looking at pi over 4 equals 1/2 times 1, right? Plus b like that. And so it comes out b equals, you guys are okay that I also just put the b on the left hand side like that? Okay? Subtracting both sides by a 1/2, so we're looking at a pi over 4 minus 1/2. Are we good there? Okay? And we can even further combine that into one fraction like that, right? And please, I don't like you guys to turn this into a decimal, so please just keep it in exact expression. It's making it easier to understand. See what I'm saying? No? Even though, yes, it may be a little complicated to write, but it's easier to understand. So combining all this into one fraction, right? And keep in mind that pi does mean an actual known value, right? We're talking about pi minus 2 over 4, you guys all agree? Yeah? Okay, so that's our b, the y-intercept. So the final complete equation here is going to be y equals 1/2 of the slope, right? X plus, and you got the pi minus 2 over 4. That whole ugly thing right there, right, is going to be your y-intercept. Okay, so let me show you guys something on the computer screen right here. All right, so this is our usual graphing space, right? And I use decimal here. It doesn't mean I'm promoting for it or anything. It's just, it's a tool that's convenient to show the graph. So, what happened to my mouse cursor? Right? So now the tangent inverse function we're looking at, f of x. Okay. Now, just want to mention a little bit, in case you haven't been aware, but for a lot of technologies, you can also type the tangent with the superscript -1 to indicate an inverse function. But for technology, a lot of times we go ARC right there, arc, tangent, that's indicating tangent inverse. Okay, it's another way of saying it. So tangent, inverse sine, you go arc sine, right? And inverse cosine right there, you say arc cosine. Right? That's the way that a lot of machines are running with that. So our function is tangent inverse of x, so we call that just arctan of x. And that's our function. Does that look to agree with what our understand so far? What we understand so far? And so now, the tangent point was found to be at 1 comma, okay, pi over 4. You guys all agree? Okay, so there's your tangent line. I mean tangent point in purple that's popped out right there. So that value was a pi over 4. That's why I hate putting that in decimal like that, right? Making it very deadly. So now let me move the graph here a little bit. So the line we have just found, y equals, right, 1/2 x, and then plus. Now you gotta see it's a pi minus 2 over 4, and there's that line that just now popped out. Okay. See? Let me put this in bold face right there. It's making it easier to view for everyone. All right. See, so just like that, our graph, the famous tangent inverse, right? And then the tangent point is here. The line in blue just now popped out. My point is, it's just the equation that we have found right here. Right? And now when we put it in with some kind of technology to precisely grab it, right? Then we got the exact tangent point. I mean, the exact tangent line being placed right at that tangent point. And I've been making it clear since the beginning of the quarter. Now, when we're getting into the concept of tangent line in calculus, tangent line doesn't hardly means it has to be strictly just going through one point. Obviously, this line does cross the graph at some other point, but I'm talking about locally, right? Like around some closed area on that graphic there, around the tangent point, and that line that is only going through at that one point. But of course, in some far range like that, it may still cross through the graph at some other point as well. It's all due to the bent nature of your graph. Okay. All right.